Verse is about solving the larger problem of the metaverse. Verse is launching an Unreal Editor for Fortnite, but we have much longer term and bigger plans for it. But essentially, it's aiming to provide a programming language solution supporting development of many kinds of games and other real-time 3D simulations, supporting a full development cycle of tools and content creation for the metaverse. I'd like to say a little bit about what we see this as ultimately, because the metaverse is more than Unreal Engine is today, and it's more than Unreal Editor for Fortnite is today. But it's about social interaction in a shared real-time 3D simulation, right? The metaverse is about the experiences people are playing today in Fortnite and Roblox and a whole lot more, and what this becomes as it evolves into a medium for billions of people. And we're talking about the metaverse as a long-term open economy. And so when we talk about what we're shipping with Verse today, we're really shipping one thing, but we're designing for a much, much longer term set of features and set of aspirations for this thing. And the metaverse, importantly, is not just another app platform, right? When you release an app, you use a bunch of libraries, but you compile one piece of code, you ship it, and it doesn't change again until you release a new version. Whereas the metaverse, we think, will be the combination of millions of objects written by millions of different developers, a lot of code, a lot of content. It's constantly being updated, in which vehicles from one developer together with characters from another developer have to work together, even if those programmers have never met each other or never tested their content before. So we're talking about a programming world that's quite different than the ones of the past, and one which requires a very robust framework supporting these sorts of usage cases. And so the metaverse needs a special kind of programming foundation, right? We want something, first of all, that's really easy to learn. We want it to be somebody's first programming language, just like JavaScript is to web programmers today. We also want a language that enables us to catch problems at development time before we've shipped content to millions of users. The costs of shipping a problem once it's already shipped are much, much, much higher than catching bugs. So we want a strongly typed language that we can count on the compiler to guide us on what the problems with the programs are before we ship them. We also want a language that's really conducive to writing lots of modules by different authors which can work together and evolve over time while maintaining backwards compatibility. So this open world interoperability is a big design goal for the entire system. We're also thinking of a programming framework which can eventually scale to massive simulations. Fortnite Battle Royale is 100 players together in a single shard, but in the future we might be able to get 1 billion users together in a single shard, and we want a programming model that can support that. We also want a language, and we've been putting a lot of effort into building a specification with enough rigor that it could be a future open standard that's agreed on and widely implemented by companies all around the industry, just like JavaScript is in a web browser today. So Verse is our attempt at this, and we're aspiring to create strongly typed language that's very recognizable to programmers who've used any of the mainstream popular languages today, whether it's C# or Python. We want something that's not too scary, but is at the leading edge of compiler technology and be able to catch problems at compile time. So there are several other principles guiding this, and we're kind of learning from the mistakes of the past. We want a programming foundation that is just code, where you're not writing code in one language that constructs queries in another language and converts them to strings and sends them off to a database and then parses the result, where a whole lot of different languages are interoperating through some clumsy interfaces. We want a single language where you can just write code that gets your job done. We also want a language that can scale to transactional programming in the future. If you think about a simulation that might scale far, far beyond the capabilities of a single node in a data center, transactions are the core technology that supported databases scaling up to huge data sets and to huge concurrency. And transactions, we think, will be the future programming model that enables code to scale up without becoming complex. We also are aiming to build a language that can do everything, supporting code in multiple paradigms, a language for data also, just like JavaScript has JSON for describing data, Verse has VSON, subset of language that can describe data accurately. And even things like markup. There's a markup language embedded in Verse. It's not usable today, but it's in the specification. It will evolve in the future. And even more advanced features for the future. We've also put a lot of effort into building a language that's to a certain extent, timeless. We have this question, what happens if we met some aliens for the first time and compared our programming languages? Well, I think we'd find that we have a lot in common, but they probably don't have 32-bit or 64-bit integers. And so we want a programming language that's free of kind of the temporary constraints of current systems. And to do this, we recognize that we're building in a very long-term evolutionary environment where we're designing a language for the very long-term future, and we've codenamed that Maxverse. And we have a massive specification written out on paper for what we want the language to eventually be. And we're working to that step by step in what we call Betaverse. This is the beta version of the language that's launching right now. It has a limited subset of those features, but we have a nice clear path where step by step we can get closer and closer to the ideal so we don't end up painting ourselves into a corner as we evolve the language, as so many others have done in the past. And we're holding ourselves to very rigorous backwards compatibility standards. Now, these are going to be relaxed during the verse beta, but when we get to the open metaverse, we really need a programming foundation where your code does not break every time a new version of your metaverse browser comes out, or that doesn't differ between different browser engines. You want something that's very stable and very reliable as a foundation for all of our long-term development plans. And so now to talk about the specifics of the language, I'd like to invite out Phil Pislow, the Director of Language Engineering at Epic. Phil?
Hey, everybody. So I'm super excited to show you verse by example. So let's just jump right in. Let's say that you want to define a value, constant value called x, and set it to the value 42. This is what it would look like. And here we've given it the type int. Although it is also possible to write this without the type. If you just say x colon equals 42, the compiler will figure it out that this is an integer. And here we're defining a constant value. Later on, I'll show you how to define values that are mutable, like mutable variables in most other languages. Here's an example of an array. Again, here I've given the type. So the type is square bracket int, which means an array of int. And the value is the three integers 1, 2, and 3. Of course, I can also do that without specifying the type, and the compiler will just figure it out. So let's get into something a little bit more complicated, functions. Verse supports a function syntax that is very similar to mathematics. So here's just a one-liner function. It'll take an x and return x plus 1. You could also put the x plus 1 on the next line. Verse supports syntactically significant indentation like Python and Haskell. So if you have an indented function body below the function signature, everything that's indented stays part of the function body. And the same is true for other block scoping constructs in the language. The language does also support squiggly braces, so you could put the function in squiggly braces if you don't like syntactically significant indentation. Verse functions can be overloaded. Here's an example of a function foo that takes either an int or a logic. Doesn't even have the same return type in both cases, could be a completely different function body. If you call foo with 0, it calls the first foo and returns a string. If you call foo with true, it calls the second one and returns nothing. Next up, modules. Modules are a great feature for encapsulation. The easiest way to make a module in verse is using the directory structure. Within your project, if you have verse files in a subdirectory, that subdirectory becomes a module. But you can also use modules directly in your code, and this is how you would do it. You use the module macro. Again, syntactically significant indentation means that the A and F members are part of that module. So here I've defined both members public, which allows code outside of the module to reference them. Verse also has structs. Structs are great for just passing around clusters of values with named properties. So here I have a struct that just has one member A of type integer. There's a couple of things going on here that I want to point out. First of all, our naming convention, which is not enforced by the compiler, is that we use capital case for values and lowercase for types. For multiple words, we use snake case for types. So maybe it would be foo underscore bar instead of just foo. And we use camel case, uppercase camel case for values. It's not enforced by the compiler, so you can do whatever you feel like, but this is what we recommend. Another thing happening here is that I have given the A member a default value of 42. So if I instantiated foo without specifying the value of A would be 42. But here, as you can see on the second to last line, I'm instantiating foo with A being overridden with the value 43. So then later when I say x.a, I get 43 instead of 42. Verse also supports classes. Classes are more powerful than structs. You can have subtyping. You can have functions. Classes also have, class instances also have identity, kind of like they do in Java and other object-oriented languages. Here I've just created a class that has no supertype called bar. I've given a field A with default value 42 and a function. And I've instantiated bar and again overridden the default value of A with 43. This is what it would look like if you did subtyping. Subtyping is the syntax for subtyping is you say class with a parenthesized clause. Whatever is inside of those parentheses is the supertype. So here, bar is the subtype, foo is the supertype. Functions are virtual by member functions and classes are virtual by default in Verse, and we require that you use the override specifier when you are intentionally overriding a virtual function. So here we've overridden f in bar to do something different than it would have done in foo, and in order to placate the compiler, we've placed the override specifier on f. Now let's talk about mutability. So far I've shown you a bunch of features where there's immutable variables, and that's not appropriate for all use cases. So Verse also supports mutable variables, and the mutable variable support is really awesome. Here's a really simple example. All I have to do is say var, and x is now a mutable variable. This means that I can change its value whenever I like. The way that I change its value is using the set keyword. Var and set, very simple. So here, var x starts out with the value 42, then I set it to 43. Later, when I say y colon equals x plus 1, the x value that it's reading there is 43, not 42. So y will have the value 44. The mutability features allow for something we call deep mutability. So here I've created a var map. So it's a mutable map that maps int to int. X starts out being the empty map. The way that I insert elements into the map is using set. So I set x subscript 42 equals 100. That makes it so that x now has a mapping from 42 to 100. Similar syntax can be used for appending to an array. So here I've got a mutable array, starts out empty, and then I push the value 42 at the end of it. That's what pushing to the end of the array looks like in Verse. Now let's talk about another feature, which is tuples. Tuples are like a very lightweight way of just taking a bunch of values and passing them around together. Here I've created a tuple that has an integer, a string, and an array. I can also give this thing a type if I want. So that's what that would look like if I spelled out the type. Tuples are mostly used as function parameters. That's the main way that you'll encounter them. So for example, if I say that there's a function f that takes two parameters x and y, what I'm really saying in Verse is that it takes one parameter, and that parameter is a tuple of type int. So if I create a tuple like 1, 2, I can use that as a parameter to this function that takes x and y, and the tuple will be flattened. But parameters are actually a little bit more complicated than tuples. They also support optional named parameters. So here, z is an optional named parameter. It's named, so what that means is that if I wanted to pass a z to function f, I would actually have to say z colon equals instead of just passing the value. And they're optional. If you don't pass a z, it gets its default value. In this case, the default value is 42. Now let's talk about generics. Verse has a very powerful generic type system. If you've ever programmed in C++, Swift, other modern languages, they also support some variant of generics. Here is a piece of code without generics. So I've created a class called thingy, and it's got an x that's an int and a y that's a string. Let's say that we wanted to add a little bit of generics to this. Here's what it would look like. So instead of defining thingy as a value that is just a class, I've defined it as a function over type. So thingy is now a function that takes a type and returns a class. And the class that it returns is a class where the y member has the type t that you passed into thingy. So here you can see that instead of instantiating the object by saying thingy and then the squiggly braces, I'm instantiating it by saying thingy and then in parentheses string and then the rest. So I'm instantiating, that tells us that we're instantiating a thingy where the t is a string. And finally, on the last line, I've made the function generic. So in the original version, the function just simply took an object of type thingy. Here, it's taking an object of type thingy with a generic type. And because I'm using the where clause, the t is inferred. So if I call the function f with some object of type thingy for any type, you can just call this function, and type inference will infer that t is whatever type you were using. Because of our aspiration to have verse be the language of a unified metaverse with everybody's code all in one namespace, Verse supports a global unified namespace with paths. The top level of a path is a domain. So here are examples of using paths in Verse today. This is basically the verse include statement. We're pulling in the verse.org simulation module into our scope, and then we're pulling in the Fortnite.com devices module into our scope. And these paths are not strings, they're actual, they're syntactically recognized within the language. And you'll see more and more of paths in the language as we develop it out. All right, now let's talk about where Verse really diverges from other languages. Verse is inspired by functional logic programming, which means that instead of relying on Booleans for conditions, it relies on success and failure. So here I've written a Verse program that first says that x is 100, and then says that x is 200. That's a contradiction, so the program will fail. And in fact, failure is the way that you do comparison in Verse. So if you run a piece of code within the condition of an if statement, what you're doing is you're asking Verse to run that code to see if it succeeds or fails. If it succeeds, then you take the then case. If it fails, you don't. So here the x equals 200 will fail because x already has a value and that value is 100, and so what will not be printed. Same thing happens if you use inequalities. So greater than is a failable expression. If it succeeds, then the if statement will print what? In this case, it'll fail. You can also abstract failure out using the decides effect. So here I've defined a function f with the decides effect, and it decides if x is greater than 100. I can call this function f with the square bracket call syntax. Square bracket call syntax in Verse means I want to call this function to see if it will succeed or fail. If it succeeds, you'll get the value. If it fails, well, you have to be in a failure context. And in this case, I'm calling f from within the condition of an if, which is a failure context. So this is the same thing as if I had said x greater than 100 inside of the if condition. And again, this will fail because I'm calling f with 0, and 0 is not greater than 100. This decides thing is an example of effect specifications in Verse. In Verse, you can specify for any function what kinds of effects it's capable of. By default, functions have a certain set of effects that you'll find useful for most cases, but sometimes you will use effects like decides to broaden the power of the function. In this case, I'm giving the function the additional power to fail if it wants to. And then a little bit later, I'll show you another effect that is popular in Verse. Okay. Now, this concept of failure is closely tied up with transactions. So if you run a failure context, in this case, the if condition is a failure context, that failure context will either succeed as a whole or all of it will fail. What this means is if you run this code and x is not less than 100, then this effect that you performed will actually never happen. I mean, it'll happen, but behind the scenes, we will roll it back as soon as we realize that this failure context is failing. Now let's look at another effect, the suspends effect, which is the way that you create coroutines in Verse. If you've ever programmed with JavaScript async functions, coroutines in Verse work sort of like that. So here I've created a coroutine, and the reason why I've done that is I want to wait for user input. So this wait for input presumably is another suspense function that I'm calling, and it might suspend for maybe multiple frame ticks or something. So if you want to wait for input, if you want to wait for another frame tick, You got to be in a suspense function, and you've got to call something that'll wait. But our coroutines are way cooler than JavaScript async functions because we've brought in all of the power of ScookumScript structured concurrency. So here's an example of how you create coroutines in Verse. On the left is the block construct, which doesn't really create coroutines. It just runs whatever the coro 1, 2, 3, 4 in sequence synchronously. But if I say sync, then these 4 coroutines will be run concurrently to one another, and the sync clause will return once all of them are done. And keep in mind that any of these things could be waiting for input, could be sleeping, could be doing whatever they want. Race is another construct. This one's really fun. Race means run a bunch of coroutines, and whichever one finishes first wins, and the other ones are canceled at that point. Rush, similar. It runs until one of the coroutines finishes, but then the remaining coroutines that took longer are allowed to finish asynchronously after the rush statement returns. Finally, the branch statement creates just a single path of asynchronous execution. So here, coro 1, 2, 3, 4 are running one after another, but concurrently to the code that used the branch. To make the race construct and this idea of canceling coroutines even more powerful, we have a defer statement. You don't have to use it in a coroutine. Here's a simple example where I'm printing hello world even though the code is out of order. The reason why this works is if you have a defer statement, then the code within that defer statement will run when the scope that you're in exits, no matter how it exits. So here, presumably after print hello, you'll return or something. So then we'll print hello, and then we'll print world, because printing world was deferred. So this is a goofy way of printing hello world using defer. But this is where the construct actually becomes useful, and that's if you use it with race. So as I said before, race will run the various coroutines. In this case, there's 2 coroutines. One coroutine is the one created by the block construct, which defers thingy and then does something slow. And the other coroutine is the something fast coroutine. As you recall, race will run until whichever coroutine finishes first, and then the other coroutines are canceled. But the defer statement ensures that when that first coroutine is canceled because it was too slow, it will run the thingy function immediately upon being canceled. So this lets you manage cancellation in your code in some way. So it's not just that your coroutine goes away, you can actually run some cleanup code. Now let me get into my favorite feature of Verse, which is the for loop. Here is a very simple for loop. I'm just using the for loop here to iterate over an array. This does what you would expect. It iterates over the elements of some array and prints all of them. But the for loop is kind of like a query. Because of the functional logic power of the language, it can do some of the things you would expect from a query language. So for example, I can throw in an additional condition here. This will print all of the elements of some array that are greater than 100. Or this will print all of the elements of some array that are not equal to 100. And you could layer these conditions on top of one another if you wanted to. Just before I show you some more crazy code, here's another simple example. This will print the integers from 1 to 200, except for 100. All right, now let me show you the really cool example. So this example is taken from a Minesweeper game that we wrote during one of our that one of us wrote during one of our Verse game jams. So to set up Minesweeper, you have to compute the adjacent mines for every cell in the Minesweeper table. And that's kind of annoying to write, because you have to iterate over all of the x-coordinates of the map, then the y-coordinates, then you have to kind of iterate around whichever cell you're in. And of course, you could be at a cell that's adjacent to the edge, so then it doesn't have all of the adjacent cells you'd expect it to, so you have to do some bounds checking. In Verse, you can write that entire loop just as a single loop without any nesting. The way you do that is first, we use the y arrow cell row colon cells construct to say, I want the index in the array and the element in the array of cells. So y is the index in cells. Cells is a two-dimensional array. And cell row is the element. So the cell row ends up itself being an array, a row of cells. But without even having to go into a deeper loop nest, I can, within that same for loop, say, Well, I want to grab the x coordinate and the cell out of cell row. So again, x ends up being the index into cell row, cell is the value at that index. So now with just those two statements, within the rest of the scope of the for loop, I have the x index into this two-dimensional array, the y index into the two-dimensional array, and the entry. But wait, it gets better. I can then use the range construct to loop even more within the same loop. Here, I'm looping over all of the adjacents, so all 9 adjacents, by just simply saying x minus 1 dot dot x plus 1 and y minus 1 dot dot y plus 1. And then when I access the cells array, notice that array accesses use the square bracket syntax. The square bracket syntax is a failable expression. When does it fail? Well, it fails if the indices are out of bounds. So because all of the things in the for loop clause are failable conditions, that if they fail, the loop just doesn't consider it, this means that the loop will automatically skip the out of bounds cases without you having to say anything about it. So that's how you write the Minesweeper setup in Verse, just in a single loop without having to use any crazy nesting, thanks to Verse's functional logic power. And with that, let me talk about some future plans. So we're going to bring lots of additional language features on top of what's already there. So right now, it is still a smaller language than what we hope for in the future. As Tim said, right now we're shipping Betaverse, and we're working incrementally towards the MaxVerse vision. Additionally, although right now the language is only built into UEFN, we eventually want to build it into Unreal Engine as well. And this isn't to replace blueprints, this is to augment blueprints. So if you love programming with blueprints, keep doing it. If you want to program in a scripting language, Verse is coming. We also want to release the language implementation under a permissively licensed open source license so that other people can use it for whatever they like, whether it's a different game engine or something not even game related. The current implementation is still early days in terms of performance, so expect lots of performance improvements to come. Also, right now we're shipping a relatively simple gameplay framework with Verse, but we're going to grow that and ship a much bigger framework in the future. And on that note, let me turn it over to Tim Tillotson, our gameplay engineer director.
Thanks, Phil. Let's talk about the Verse API. So much of what I will share today is really forward-looking. We have a lot of plans of what we'd like to do, a lot of things we prototyped. The API is currently in beta and will be for a long time. We strive to have a public, stable API, but we reserve the right to change things throughout beta as we need to. If we deprecate things, we'll try to do it like we do with UE. We'll do it in phases, or we'll provide some easy way for you to kind of upgrade your code. So this is kind of a comparison with the game Metaverse to the World Wide Web and how we envision it. At the high level, we want to make creating user games and simulations as easy to do as it is to create web applications today. But to do that, you have to have kind of this common set of APIs you're building on top of. And so initially, though, those APIs often start out very custom to the browser or the simulation engine that's created. So we saw a lot of things with web browsers. You would find kind of very custom APIs, but eventually you find an open spec that many of them implement, so it's easier for people to write applications against. We envision the same thing will occur here in the games and simulation space. And eventually you'll have users build their own custom community APIs on top of that. And so we start with this phase where we have proposing kind of your individual standards that you implement that solve the problems you need to solve. An example is Quick was implemented by Google and Chrome back in 2012 to speed up how the browser talked to their web search engine. And then that became the basis for HTTP3 almost a decade later. So we're proposing Verse as an open standard, and we'll hope that also becomes adopted along with many of the other 3D standards we have out there for scenes and 3D models. Much like the JavaScript VM empowers a lot of the web content logic, the Verse VM, we envision, will empower a lot of the game simulation type logic. And we open it up for others to use in those same game simulation engines as well, beyond Unreal. And we also want to abstract a lot of the hardware-isms so you can focus really on making the games and what you do best. So talking about the API we have today, really the initial API is built around Fortnite Creative. And so these are just a variety of the different genres that people have created games inside of Fortnite Creative today. And the scriptable device is kind of how we're first connecting Verse to Unreal and to Fortnite. As you look forward over the course of this next year, we want to allow you to also script components, so you can build up individual objects and build scenes and build much richer, deeper experiences. We also plan to add a bunch of features which will enable new things that are more challenging to do today with the limited API we provide. Looking forward a year or two, we also want to make Verse performant and work on gameplay systems, so it's easier to do things like physics, custom vehicles, those kind of deeper, high-performance operations. But long term, we really want to make Verse able to run AAA games. And so there's a lot of work we have to get here. And before we'd recommend people using Verse and UEFN and say a AAA game, we want to do that inside of Fortnite ourselves. And so we've got years of work ahead of us to do that. But there may be places where a AAA game would want to say, okay, let's make a limited experience to expose our IP to the millions of Fortnite players. And so a lot of opportunity here for us to decide what's the right time for you to jump in and try out Verse and then use it in your games. So there are a few differences between UE and UEFN on how our guiding principles work. First of all, a lot of times in UE, you have to go and decide what you want to replicate, write a lot of code that kind of connects pieces together. With UEFN and Verse, everything is replicated from the get-go. So it's simple to approach, very easy to kind of jump in an hour of code, write something that is playable. We want to be able to constantly evolve. So Fortnite, we update every 2 weeks. We want to be able to update games very quickly and let people kind of iterate in that space with their players. We want to have this world where people can publish something and someone else can use it and kind of have this back and forth iteration occur, much like happens in the web space. And so this really rapid iteration of game content is what we want to enable in this space. So at a high level, we divided the Verse API into 3 namespaces. There's verse.org, which contains kind of the game-agnostic APIs that we will submit as part of open specs. There's unrealengine.com, which contains kind of the spatial math UI, those types of things which are very specific to the Unreal Engine. And then there's Fortnite.com, which is the APIs that are largely specific to how Fortnite wants to do certain things like vehicles or characters. And those will largely always be kind of contained inside of Fortnite and UEFN. So this represents roughly the high-level overview of where the APIs exist today. So if you download the Unreal Engine for Fortnite, this is where you'll see kind of the APIs exist. Inside of verse.org, you'll see math, containers, colors, and things that are agnostic for a game engine, but are generally in use in simulations like player and team. UnrealEngine.com, we have things like diagnostics. Most of our diagnostics today and debugging really is kind of this printf-based diagnostic debugging. We pipe that from the servers down to the editor so you can at least see it in real time what's going on in your game simulation. Long term, though, we have other plans to improve that quite a bit. The Fortnite API right now is really around these creative devices. We have a few things we've exposed with characters and vehicles, but there's a lot more we want to express in the future here. And in the very near future, we plan to expose the ability to script AI. So I want to look a little bit further out what we plan on doing this year as well as in the future. And so I went to one of the indie showcases last night where you get to play a lot of games. And I would say there's only a small percentage of those you could build in UEFN today. And that's because a lot of them want things like persistence. They want things like basic input and camera control. And so these are the type of features we want to add over the remainder of the coming year. But the majority of our internal tech focus is going to be around this scene graph. We want to let people build prefabs. We want to let people customize weapons and abilities. We want to let people put scripts on objects, and build out scenes. And so enabling this really rich environment for people to kind of share and build content. And then adding things like debuggers, performance profiling, and also analytics so you can see what players are doing with your game. So a little bit detail into what we're looking at on the scene graph and some differences with maybe other scene graph implementations that are out there. The most important is we are looking at how we can have a public API that you basically say, here's the things I want other people to be able to query in the scene graph. And these are the things that I want to keep internal so we can iterate on internally and change it next version and not have to worry about breaking anybody who's using our API. On the research side, we're looking at things that you find in UE like level instances, layers, variants, other ways in which we're composing content today, and see if there's better ways we can merge and undo those operations, both in design time as well as at runtime. Ideally, so you can make changes to your scene dynamically, much as you have like web styling today on web pages. So I'm going to walk through kind of a demo of adding verse code to a Fortnite creative game, or in this case, a new UEFN game. So you create a new verse device by inheriting from creative device. In this case, I've created an escape sequence device. And the Fortnite creative devices today are just this bundle of logic that you kind of drag into the scene. as an object. In this case, you'll see kind of this little console here that represents your script. Inside of the script, you can add editable properties. In this case, we have a player spawn that shows up as a property in the scene that you can then modify on a per instance basis. So once you've created that class, then you can override the onBegin method, or in this case, because it has a suspense effect, it's a coroutine, and then add your own custom logic. In this case, we'll spawn an escape sequence that the player will then run through. So in this case, a little bit into the race method that Phil talked about, I have the escape method we run, and then we're also waiting for the player to respawn. And so in this case, the escape sequence shows a message, and then if the player respawns, we run the defer block to hide that message. And so you'll see in the game later, little demo that I run through here, that pretty much any place in that, we should be able to have the player respawn, and the defer blocks will cause it to kind of reset and be ready for the player to start that sequence again. And so these defer blocks can be composed in nice ways so that you'll notice they actually go back up the stack. And so the last defer block that was run or placed on the stack will be the first one that's run. So little caveats about the scope of this demo. This is based on the Verse Parkour game template, which is in UEFN today. All the code and level edits are made entirely by me, so lots of programmer art. A lot of things aren't polished like an artist would do. I've imported a few small sounds and VFX. But I expect that the experience I've shown you, will show you here, is roughly what an experienced developer who knows UE, knows the tool set inside of UEFN, and is familiar with verse code will be able to do in roughly a day or less. So here we tell the player to go grab the stolen files, give them a little indicator to show them we're on level, and the way for them to enter that area. So once they've grabbed the files here, now we delete the file and then spawn some AI to harass the player, and then wait for them to enter the rooftop area. Once they've entered that rooftop area, we spawn some more AI to continue harassing the player. We start the building on fire, and then wait for them to trigger one of these other conditions. In this case, they've entered the safe area, and then prompt them to enter the getaway vehicle. This could be many branching conditions you have in gameplay code. I've only done a simple one right here. So once they jump on the car here, the getaway vehicle, I basically have a little scripted animation we play. I play a custom cinematic cutscene here as well. And then give them the option to jump in a helicopter. And if they do jump in this helicopter zone, we'll place them in the seat of the helicopter and wait for them to enter the level outro area. And then when they do, we play the outro cinematic. So that's just a small sample of what's possible with Verse and UEFN today. And this is part of just a much larger ecosystem. You know, please see all the other UEFN announcements they've made about ecosystem and other things that we're enabling in Fortnite. We have years of development work planned. I've only talked about a very small portion of what's on our slate. But really, we want to iterate with Verse and with UEFN as you as a community. You know, now the tools are out there. There's so much we have planned. We really want feedback as we go through and iterate in this space. So I'll give a shout out to the team that has worked with us over the last couple of years to bring these things to you. And now we'll turn the time over for Q&A. And invite everyone else back out on stage here, along with Andrew Schneidecker, one of our Verse developers.
So let's see, there's a, yeah, go ahead.